Welcome. We are so glad you're here again. The Drawdown and Ignite webinar, The End of Normal, Understanding and Correcting Earth's Troubling Climate Trajectory. It is now time for me to introduce Dr. Kate Marvel. I feel like I need trumpets calling out to the world. Kate, we're so glad you're here. Kate is a senior climate scientist with us at Project Drawdown. Before joining us, Kate spent 7 years as a research scientist at the NASA Goddard Institute for Space Studies. She's a former cosmologist, and she received a PhD in theoretical physics from Cambridge University, where she was a Gates Scholar. She serves on the chapter leadership team of the 5th National Climate Assessment, and Kate's book, Human Nature, will be published by Echo Press in 2024. Take it away, Kate.
Hi, folks. Thank you so much for joining. I am so excited to be here. So excited to talk about my favorite thing in the world, which is Earth, and my second favorite thing in the world, which is science. So let's get started. All right. So let's just get straight into the science. So newsflash, the world is warming. Global temperatures are now around 1.2 degrees Celsius. That's more than 2 degrees Fahrenheit hotter than they were on average before the Industrial Revolution. So the climate is changing, and we understand why. Now, there's a certain group of people who love to point out that, oh, climate has always changed. And they tell this to climate scientists, and we're like, we know, we told you that. But it's true that the planet has been very different before in its history. Take, for example, the last glacial maximum, or the last ice age. 21,000 years ago, where I'm sitting right now in New York City would have been covered with a sheet of ice. Most of the places where a lot of folks are streaming in from would have also been covered with ice. And that's because it was between 5 and 6 degrees colder than it is now. And we know what caused this. We all know that the Earth goes around the sun. But we're not alone in the solar system. There are other planets, there are moons, and the gravity of all of these things pulls on us very, very slightly. And what this does is it makes our orbit change and change back again over timescales of thousands or hundreds of thousands of years. Our orbit can go from a circle to an ellipse and back again. The tilt of our axis can change a little bit, or the location of the North Star can change from Polaris to Vega and back again. And we know that the last ice age was caused by a change in the tilt of the Earth's orbit. But gravity didn't end with the ice age. So it's reasonable to ask, is climate change now due to changes in the Earth's orbit? Well, in a climate model, we can do that counterfactual experiment. We can ask what the Earth's temperature would look like if the only thing going on were changes in the Earth's orbit. And the answer is, it does pretty much nothing. So it's not the orbit that's causing climate change today. But could it be the sun? We know that the sun's luminosity changes. There's a sunspot cycle, which goes roughly every 11 years, and the sun gets a little bit brighter and a little bit dimmer with time. So is it the sun? Now, as Elizabeth mentioned, I spent many years working for NASA, and I believe that if the sun were getting noticeably stronger, somebody at NASA would probably have noticed. The sun and changes in the sun cannot explain the warming that we've seen so far. So it's not the sun. But there are other things that nature can do that can and do change the climate. The eruption of the volcano Krakatoa in 1883 put so much gas and dust and ash in the atmosphere that it led to widespread cooling. It also led to really spectacular sunsets, which influenced the art of that era. But that wasn't the last volcano to go off. Mount Pinatubo in 1991 sprayed so much ash and gas and dust in the atmosphere that it cooled the entire climate by about 0.5 degrees Celsius. So is it volcanoes causing global warming? So volcanoes do change the climate. They have short, localized cooling effects. You can see here Krakatoa in 1883, and then more recently, Agong, El Chichon, and Mount Pinatubo in 1991. But what they don't do is make the temperature gradually increase over many, many years. So no, it's not volcanoes. What about things that humans have done? Well, one of the most noticeable things that humans have done, one of our largest impacts on our planet, has been agriculture. So about 40% of the Earth's surface that's not covered by ice is currently being used for agriculture. And that means that we have cut down a lot of trees. And cutting down forests changes the surface of the Earth because it takes something that was once dark and very absorbent, and it replaces it with pasture, with cropland, with cities that are shinier and more reflective. So this changes the shininess of the Earth, what scientists call the albedo. So is deforestation responsible for the warming? Now, accounting for the albedo changes or the increased shininess due to deforestation, we can see that globally land use change has had a very slight cooling effect. So no, it's not deforestation that's been warming the world, or at least not the albedo effect of deforestation. But deforestation does more than just change the shininess of the Earth's surface. When trees are cut down, carbon dioxide is released into the atmosphere. Greenhouse gases are also emitted by industrial processes. When we make steel, when we make plastic, when we make cement, we release greenhouse gases, even if we don't burn any fossil fuels. And finally, obviously, as we all know on this call, greenhouse gases come from the burning of fossil fuels. Now, fossil fuel burning is the primary and a very, very important source of greenhouse gases in the atmosphere, but it is not the only human activity that produces greenhouse gases. Roughly a third of our greenhouse gas emissions come from land use and industrial processes. So human beings have done things. Human beings have cut down forests, burned fossil fuels, and made stuff. And these activities have emitted greenhouse gases. So if you take that history and translate it into emissions of greenhouse gases, that becomes a story that you can tell to a climate model. And the climate model tells you a story in return. But if you only tell it about greenhouse gases, it warms, but it warms a little bit too much. So greenhouse gases warm the world, but they seem to over-explain the warming that we've measured. So is this because we've got them wrong? Is this because we've somehow overestimated their warming effect? No, not necessarily. It's because human beings have done more than just put greenhouse gases into the atmosphere. We can see some human activities from space: polluted haze, the tracks left by ships as they cross our oceans, smoke from wildfires that humans have started. And what you see here are tiny particles. These tiny particles are called aerosols. And aerosols affect climate both directly by blocking sunlight and indirectly by seeding clouds, which themselves block sunlight, which you can see in the ship tracks picture. And aerosols have a very strong cooling effect on the planet, not strong enough to cancel out the warming due to greenhouse gases, but enough to mask it a little bit. So aerosols cool the world. Now, if you put it all together, you'll see that you need a more complicated story of human influence to explain the warming that we've seen so far. Humans have done things that have emitted greenhouse gases and aerosols. We've also affected the surface of the land. So together, these things pretty much completely explain the warming that we've experienced so far. So this is data generated from the model that I worked with in my previous position at NASA. And we collaborated with Bloomberg to develop this visualization of our data, which Elizabeth is going to put in the chat if anybody is interested in accessing it and playing around with it a little bit. But what I hope that you can see here is that climate models run on stories. Sometimes those stories are counterfactuals. What if we didn't exist? What if the sun was the only thing that was changing? And sometimes those stories are true. This is the history of the world, which we've translated into emissions of greenhouse gases and aerosols. So if you tell a model a true story, it will tell you what really happened. So we know it's warming and we know why, but what does it actually mean when the Earth starts heating up? Because nobody lives in the global average. And on winter days, it can be really tempting to say, well, a couple of degrees, what's the big deal? That sounds even pleasant. But we know, as we have experienced this summer, that climate change makes heat waves hotter, longer, and more frequent. So why is this? Well, the first explanation is a really simple one, a simple thermodynamic argument. We're putting more heat in the system, it's hotter on average, so we would also expect to see more extreme heat waves too. But there's compelling arguments in addition to a thermodynamic change that we're also seeing dynamic changes. We know that the Arctic is warming faster than anywhere else on Earth. And the large-scale circulation of air through the atmosphere is really driven by the temperature contrast between the Arctic and the tropics. So that's making the jet stream wavier and allowing heat domes to form more easily and perhaps linger for longer. And finally, there's another thing going on. When you get hot, your body covers you with liquid water in the form of sweat. And that has a cooling effect because it takes energy to turn a liquid into a gas. So evaporation cools a surface. As the Earth gets hotter, more water gets evaporated away from the surface and it gets drier. Now, very, very dry ground has lost its moisture. So it can't sweat, it can't cool itself off by evaporation. And this in turn makes heat waves hotter. This is something that we call the soil moisture feedback. And this is one of the reasons why climate change increases the risk of drought. That's because warm air is thirstier air. Evaporation increases as the temperature increases. So even if there are no large-scale changes in rainfall patterns, and I want to be clear, that is a big if, increased evaporation can dry out the surface just because of that temperature change. And that can lead to dry soil moisture and agricultural drought. But all of that evaporated water has to go somewhere. And that's why we expect that climate change will lead to more heavy precipitation, more flood risk. Now, in general, that's because there is more rainfall in a warmer world, because that evaporation has to go somewhere. But extreme rainfall is actually rising faster than average rainfall. And this is because of another thing that physicists understand very, very well. Warm air holds more water vapor, up to 7% more per degree Celsius of warming, or 4% per degree Fahrenheit of warming. And what this means is that when it rains, it pours, because there's simply more moisture in the atmosphere that can be dumped on us in the form of extreme rainfall. Climate change also means sea level rise. And this is happening for two main reasons. First, right now, water is locked up on land inside ice sheets or mountain glaciers. And when those melt, the water goes from the land into the ocean, raising the sea levels. But there's another thing going on too. Warm things expand, and warm water is no exception. So the ocean waters are getting warmer, warm water expands, and this is also contributing to sea level rise. Climate change also makes hurricanes stronger, if not necessarily more frequent. Why is that? Well, warm water is hurricane food, and rising sea surface temperatures are the fuel for stronger storms. We also know that because warm air holds more water vapor, there's more moisture in the atmosphere that these storms can dump on us. The rainfall totals, for example, that Houston saw during Hurricane Harvey would have been nearly impossible without climate change. And as sea levels rise, the storm surges associated with these hurricanes can become more dangerous, pushing further and further inland. Now, fires are extremely complex. They depend on many things. They depend on the availability of fuel. They depend on ignition, whether lightning or human actions, and they depend on suppression. The damage that fires cause depend on who lives where and how well protected they are. So fires are really, really complex, but we do know that fire weather, which are the hot, dry conditions that make fires more dangerous or more likely, that fire weather is increasing in many places. And the reason for that increase is climate change. So to recap, we do know a great deal. We know a lot. We know the world is warming, and we know why. And we know a lot about what it means when the world gets warmer. We know that a warmer world has more and deadlier heat waves. We know that it has heavier downpours. We know that the sea levels are rising. We know that warmer sea surface temperatures are fueling stronger storms, which are surging farther inland. But I am a scientist, which means I love to think about and talk about the things that we still don't know. Now, I want to be really clear here. Uncertainty is not the same thing as ignorance. We don't know everything, but that doesn't mean we know nothing. But let me talk for a little bit about some of the uncertainties, some of the many things that we scientists still don't know. One of the things we don't know is a really, really basic question. We don't know how hot it will get. The future scenarios used by the climate modeling community, those are these very confusingly labeled colors over here on the side of the map. They project anywhere from between 1.5 degrees of warming to almost 5 degrees. So just to put that in perspective, remember 5 degrees was roughly the difference between now and the last ice age. Now, what should we expect? We don't know. And there are several reasons why we don't know exactly what to expect. First, we don't know how the Earth responds over the long term to elevated levels of carbon dioxide in the atmosphere. And that's simply because we have never done this experiment before. We've never kicked the Earth this hard. And we know that temperature changes can change other aspects of the climate system. And those changes can themselves feed back onto the temperature change, making it worse, making it better. So perhaps for me, the most intuitive feedback is something we call the ice albedo feedback. We know that ice is shiny, it's reflective, it turns back a lot of sunlight that would otherwise get to the Earth and warm it. Now, as the temperatures increase, we lose the ice melts, and it reveals darker ground or water underneath. So this is an example of something called a destabilizing feedback, where warming leads to changes in the climate system that themselves make the warming worse. But this is not the reason we don't understand how hot it's going to get. Scientists pretty much understand that as it gets hotter, ice melts. What we don't understand, at least not completely, is what clouds are going to do. Any changes to clouds, their location, their opacity, their height, their amount, that affects either how much sunlight they can block or how much heat they trap from the Earth's surface coming up. And that makes clouds the wild card. Cloud feedbacks are the reason we don't know for sure how hot it's going to get. We do know for sure that clouds are not going to miraculously save us by somehow organizing themselves to stop the warming. And right now, our best guess is that for every doubling of carbon dioxide in the atmosphere, the Earth will warm about 3 degrees Celsius. But there is still a great deal of uncertainty there, and clouds are one of the main reasons. But that is not the only source of uncertainty when we think about how hot it's going to get. We don't know how hot it's going to get because we don't know how much carbon dioxide is going to stay in the atmosphere. We don't know how the carbon cycle is going to respond. Right now, humans are emitting greenhouse gases. Human activities are emitting carbon dioxide, but also methane and nitrous oxide. And these emissions come from a wide variety of sectors. The biosphere, forests, grasslands, phytoplankton, things that photosynthesize, is responding. Humans have put greenhouse gases in the atmosphere, and the biosphere has responded by taking up more carbon dioxide. Not all of the carbon dioxide that we put in the atmosphere, a great deal of it is lingering there, causing warming. But the biosphere has organized itself to take up more carbon dioxide as carbon dioxide concentrations increase. And there is no guarantee that this is going to continue in the future. We could see wildfires or desertification reducing the amount of carbon plants on land could take up because it is really hard to photosynthesize when you're on fire. We don't know what's going to happen to phytoplankton in a changing climate. And some of the things that we do know are really scary. When it gets warmer, permafrost thaws, and this releases methane and carbon dioxide into the atmosphere. Now, these carbon cycle feedbacks are highly uncertain, especially as emissions increase. We simply don't know what's going to happen in a very high emissions world. But finally, the scariest thing about the future is that we can't predict exactly when we might exceed a tipping point in the climate system. So what do I mean by a tipping point? Well, it's essentially a point of no return, a change in some aspect of the Earth system that we can't fix, at least not in a human lifetime or on timescales relevant to human civilization. Examples of tipping points could be the loss of the Greenland or West Antarctic ice sheets, They could be die-offs in forests, whether the Amazon rainforest or the boreal forest. Or they could be circulation changes, like a shutdown of the Atlantic meridional overturning circulation or disruptions in the global monsoons. And the thing that I want to stress about these tipping points is there is a great deal of scientific uncertainty in when they will be triggered, when they will be exceeded. We don't know exactly when any of these changes may be set off, only that the risk increases with warming. We are not safe, even if we manage to stay below the 1.5 degrees Celsius target. But conversely, we are not doomed if we exceed the 2 degrees Celsius target or any other target. And that's because nature does not think in degrees Celsius. These targets are just that. They're targets that humans have set. Every 1/10 of a degree matters. Every ton of greenhouse gas that we don't emit matters. Because finally, that brings us to the final largest source of uncertainty. We don't know how hot it's going to get because we don't know what humans are going to do. So you remember this graph and its confusing labels? These correspond to different possible future scenarios, different stories that we tell a climate model. Let's do a rough translation of these labels here. The red scenario on top corresponds to a future of heavy fossil fuel use, no climate policy, and resulting very high emissions. The blue scenarios down here correspond to futures of sustainable development and very strong climate policy. So how hot will it get? Yes, there is a lot of uncertainty in the science, a lot of things that we don't understand about a rapidly warming planet. But ultimately, the answer is up to us. How hot can it get? That's in our hands. I don't like this orange future up here. I don't like this future of no emissions cuts and dangerous warming. But right now, that's the first draft of the future. And you know what? I am writing a book right now, and I can tell you that the first draft of anything is bad. You need to change it. We need to change this. So you may have heard that the future is not in our hands, that we should give up because we've already doomed ourselves to substantial warming. But this is simply not true. When we stop emitting greenhouse gases, our best guess is that warming will stop. Now, why is this? I'm going to have to dig a little bit into the science here, so forgive me for nerding out a little bit. There's two competing processes at work here. First, we have to understand a little bit about the ocean's role in the climate system. The vast majority of the heat that humans have added to the climate system has gone into the ocean. We are adding the equivalent of 5 nuclear bombs worth of heat into the ocean every second. If the ocean were not there, we wouldn't be looking at 1.2 degrees Celsius of warming right now. We would be looking at 30 or 40 degrees Celsius of warming. So the ocean has been taking up a lot of heat. Now, when we reach net zero, the rate at which the ocean takes up heat is going to start to slow as the climate system adjusts itself to a new equilibrium. And this is going to have a warming effect. And if atmospheric carbon dioxide concentrations remained constant, this would mean that we could expect substantial committed warming, more warming in the pipeline. However, something else is going on. Once we stop adding greenhouse gases to the atmosphere, something else is going to happen. The things on the land and ocean that photosynthesize, the biosphere, will take carbon dioxide out of the atmosphere. And at net zero, we won't be putting it back in. So atmospheric carbon dioxide levels will slowly but steadily start to decline. And these two things, the science says, will essentially cancel each other out. So the best estimate of the warming in the pipeline is 0. The science says that right now, when we reach net zero, the warming will stop. So what do I mean by net zero? Well, net zero is defined as the point in time when any greenhouse gas emissions are balanced by carbon removal. So to understand what we mean by net zero, we have to understand what we mean by greenhouse gases, because human activities emit multiple greenhouse gases. Over long timescales, the breakdown of greenhouse gas emissions looks a little bit something like this. Carbon dioxide dominates, but there are substantial contributions from methane, nitrous oxide, and F gases. Now, the most prominent greenhouse gas is carbon dioxide. And the really important thing to know about carbon dioxide is that the carbon dioxide that's not taken up by the biosphere stays in the atmosphere. It hangs out for many decades, many centuries even. So carbon dioxide stays in the atmosphere a really long time. And that means when we're talking about warming, it is the cumulative emissions that matter. Some of the carbon dioxide emitted at the beginning of the Industrial Revolution is still there in the atmosphere, still hanging out, still causing warming. So today's emissions are just adding to this huge pile of accumulated carbon dioxide. But carbon dioxide is not the only greenhouse gas that's emitted by human activities. Methane is also a planet warming gas. Now, methane is emitted by agricultural activities, things like cow burps, things like flooded rice fields. It's also emitted by the fossil fuel industry. Natural gas, and I'm putting that in scare quotes, is methane, and leaks from wells and pipelines are really big sources of methane emissions. Rotting matter in landfills is also a source of methane. And the thing to know about methane is that it is potent. It's more than 80 times more powerful than carbon dioxide. But unlike carbon dioxide, methane gets removed from the atmosphere by chemical reactions in about 12 years or so. So methane, extremely potent, relatively short-lived. What about nitrous oxide? Well, this is a small but important contributor to warming, and it's primarily emitted by fertilizer application, nitrogen fertilizers on croplands. And the bad news about nitrous oxide is that it is 273 times more powerful than carbon dioxide. The worst news about nitrous oxide is that it stays in the atmosphere for over a century. So nitrous oxide accounts for less than 5% of global greenhouse gas emissions, but it is both potent and long-lived. And finally, F gases. These are synthetic gases that are often used as propellers or coolants in refrigerators and AC units. And they're very potent. They hang out in the atmosphere a pretty long time. But the good news about F gases is that the nastiest ones, the most potent ones, were recently banned by the Kigali Amendment, which was ratified last year by a bipartisan majority in the US Senate. So some of these emissions, particularly agricultural methane emissions and industrial carbon dioxide emissions, are right now pretty hard to abate. We also have that problem of legacy emissions, of the carbon dioxide that's already emitted hanging out in the atmosphere for a really long time. So we need to cancel these out by removing carbon dioxide from the atmosphere. So practically net zero greenhouse gases means net negative carbon dioxide. And this means that carbon removal is likely part of the solution, but it will only ever be a very, 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 very small part of the solution. Why small? So let's look at how we would actually remove carbon dioxide from the air practically. Fortunately, nature is pretty good at removing carbon dioxide from the air. Plants and phytoplankton remove carbon dioxide from the atmosphere through photosynthesis, which nobody will ever be able to convince me is not magic. Some ecosystems are really, really good at this. Seagrass meadows, coastal mangroves, tropical rainforests. And certain agricultural practices like cover cropping, no-till agriculture can enhance the ability of the soil in which plants grow to store carbon. But the thing about plants is that they don't exist to take care of humans. They don't exist to fix human mistakes. They exist to exist. And when they are done with life, they are done storing carbon. They could return that carbon to the atmosphere gradually as they decay, or suddenly in a forest fire. They also take up land. It's been estimated to offset US emissions, just US emissions, not global emissions. We would need a forest the size of the state of Texas. And there's also limits to how much carbon dioxide can be stored in the soil. So don't get me wrong, please. I love trees. I think we should have more of them. I think we should take much better care of the ones that we have. But we can't plant our way out of climate change without making other changes. What about engineered solutions? Well, humans know how to remove carbon dioxide from the atmosphere. NASA has had to think about it for years, because if you take astronauts and shut them up in a tiny little module and launch them into space, you have to think really hard about how to get rid of the carbon dioxide that they exhale before that poisons them. This is a major plot point in the movie Apollo 13, which I recently rewatched and actually really holds up after all these years. So we know, theoretically, how to remove carbon dioxide from air. And you can use really similar technology to do what we call direct air capture, sucking carbon dioxide out of the air. And people are doing it. But the thing to note is that carbon dioxide in the atmosphere is much more diffuse than it is inside a tiny little cramped spaceship. And so you have to use a lot of energy to suck it out. So that's why people are also looking at things like trying to speed up the geological carbon cycle through enhanced rock weathering, or by hacking the ocean, usually by shocking it to change its pH, or by just dumping a lot of antacid in it to make ocean acidity better and force it to take up more carbon dioxide. And all of these, to varying degrees, have promise. They're all pretty cool science. But I think we need to be really clear. A little perspective is in order. Right now, the largest direct air capture plant that's currently in development might eventually, if everything goes according to plan, be able to take out 1 million tons of carbon dioxide out of the atmosphere. And 1 million sounds like a really, really big number. But for reference, global carbon dioxide emissions last year were 40.5 billion tons. And so that means that a direct air capture plant will use an enormous amount of energy and resources to remove 0.0025% of global emissions. And as I mentioned, it's those cumulative carbon dioxide emissions that matter for warming. And if you add up all of the carbon dioxide that humans have put in the atmosphere, you will find that it weighs over 1.5 trillion tons. So let's put that a little bit into perspective. The CO2 that humans have put in the atmosphere weighs 25,000 times more than every human on Earth put together. In fact, it weighs more than 3 times as much as all life on Earth put together. There is a lot of carbon dioxide accumulated in the atmosphere. So yes, it is worth pursuing these technologies. Yes, we will need some carbon removal to balance out emissions from hard to abate sectors or try to address legacy emissions. But we need to be really clear that carbon removal is not going to enable a high emission status quo. It is not going to save us without additional action. Now, there's one more thing that we could do to hack the planet. We know that when certain types of volcanoes erupt, like Pinatubo, Krakatoa, they block the sun, they cool down the earth. So what if we didn't wait around for a volcano? What if we were a volcano? And there are different ways to do this. We could directly mimic a volcano by injecting aerosols, gas, dust, ash into the stratosphere, just like volcanoes do. We could also mess around a little bit with clouds. We could try to make those high, thin cirrus clouds a little bit thinner to prevent heat from escaping. We could also try to brighten low, thick clouds over the ocean and make them block a little bit more sunlight. And the thing is, these methods would work for a particular definition of work. They would almost certainly lower the temperature of the planet because that's what happens when you block a substantial amount of sun. But it's important to note that solar radiation management, these sort of geoengineering technologies, do not work by lowering emissions. They work by blocking the sun. And it turns out that a lot of things on Earth really like the sun. Solar heating drives the winds and the water cycle. Plants really like sun for photosynthesis. It affects cloud cover. Certain stratospheric aerosol injection methods might have really severe consequences for the ozone layer. And if we scattered a bunch of ash and dust in the stratosphere, that could change the color of the sky, turning it from blue to a pretty persistent bright white. And aerosols, those particles of gas and dust, they don't stick around for very long. In the lower atmosphere, they get washed out when it rains. In the stratosphere, they stick around for a little bit longer, but not too much longer. So if humans decided to do this, we would need to keep it up indefinitely. And if we stopped, we would risk what's called termination shock, where we would see practically decades worth of global warming compressed into a single year or even a few months. And that would be an incredibly dangerous outcome. So blocking the sun is a risky maneuver. To limit warming, the best way to do that is to achieve net zero. And it is not possible to achieve net zero without cutting emissions dramatically. And the longer we wait, the more dramatic these cuts would have to be in order to achieve our goals. So if we had started making cuts 20 years ago, we would not have such a hard road ahead. So in 2020, if you remember that year, I personally have blocked out most of it, but most of the world shut down, travel was severely curtailed, many industries were curtailed, and as a result, emissions fell by 7%. To limit warming to 1.7 or to 1.5 degrees Celsius, we would need to cut emissions by more than 7% every year. But I have good news. The good news is that we know how to do this. We have the solutions we need. And those of us here at Project Drawdown are working on evaluating them, implementing them, thinking about how they fit into the story of the future that we want to tell. Now, there is some bad news, which is that even if we implement these solutions, even if we do everything right, it's going to take a very long time before we see action paying off in the climate. So even if we reach net zero by the middle of the century and limit warming to 1.5 degrees Celsius, the climate is going to look relatively similar to the worst case scenario for the next few decades. But it is more than worth doing this for the future that our children and grandchildren will live in. It will really, really matter to them. But I don't just want a better life for my children. I want a better life for me. And the thing to note is that fossil fuel burning emits both greenhouse gases and aerosols. And aerosols don't just have an effect on the climate. They pollute our air. They affect our health. Worldwide, more than 11% of deaths are attributable to air pollution. And it's been estimated that fossil fuel phase out, which is a climate solution, which we advocate for here at Project Drawdown, fossil fuel phase out will save between 3 and 4 million lives every year. When you cut out fossil fuels, that air pollution, it goes away. It goes away immediately, or at least the next time it rains. And so these benefits will be experienced not just by our children and grandchildren, but by us in our lifetimes really, really soon. That's not all. We know that supporting sinks, supporting carbon dioxide sinks, can also help us protect the ecosystems that we love and upon which we depend. And it turns out that climate solutions have many, many, many associated benefits, most of which we will accrue within our lifetimes. So what does the climate model show you about the future? It depends on the story that you tell it. A climate model is very literally a world building machine. It shows you the worlds that were, it explains the world it is, and it tells you about different speculative futures that might be. Now, I want to reiterate that climate models run on stories. And most of the stories that we grew up with follow the same basic structure. There's a leap into the unknown, there's trials and tribulations, there's a really low point, and then there's a triumphant return. And these stories, this structure is very satisfying because the characters don't just give up when things get hard. But these stories exist because the characters decide to go on the journey in the first place. So wherever you are on your climate journey, I'm really grateful you're here. I'm so glad that you have decided to cross that threshold. So there's a lot we can do. We can build a better world. So let's get to work. Thank you so much.
Oh, yes. Let's give Dr. Kate Marvel so much gratitude. Kate, do you see all those emojis flying through cyberspace? Look at that. Thank you. There you go. Oh, thank you so much. What an absolute pleasure to learn from you today. Thank you so much, Kate. And thanks to all of you for being here. Lots of love in the chat. Also, folks sharing gratitude about what a fantastic presentation it was. Everybody who is zooming in from all over, please feel free to put chat, excuse me, please feel free to put questions in the Q&A. We have Todd behind the scenes who's working to organize them in a sheet that I'm going to look at over here and toss some questions to you. Are you ready for some questions, Kate?
I'm ready. Bring them on.
I got it. Okay. Well, I'm going to parrot some incredible questions from the audience. There are some questions about tipping points And folks are curious about how the climate scientist community, of which you are an incredible member, how the community is adjusting its models to take into account tipping points, and how you talk to integrated models used by economists to estimate damage functions.
Right. So there's a lot of layers to that question. So I think it's really important to differentiate between the models that economists use to say, this is what emissions could look like in the future. This is what the economy could look like in the future. This is what the energy sector could look like in the future. Those are called integrated assessment models. And I think the thing to note is that those models are really hard to build. They're hard to build because they are distinct from climate models. So a climate model is very well behaved in a sense because everything in it obeys the laws of physics. You've got air, like little molecules of air, you've got little droplets of water, you've got ice, you've got dirt, and all of those things act as physics dictates that they do. There is complexity in a climate model that comes from the fact that all of this physics is interacting with each other. There's just too much physics in a climate model. But fundamentally, everything is obeying defined, understandable equations. People don't do that. People do not follow the laws of physics. People are confusing and they are difficult and they are hard. And that is why social science is harder than physical science. Integrated assessment models are based on social science. They are based on estimates of what people who do not follow equations are going to do now and in the future. And so integrated assessment modeling is just a much, much harder exercise than climate modeling. So those scenarios, those stories that I showed that we feed into climate models, those come out of integrated assessment models. I, as a physicist, don't have any way to evaluate the assumptions and the modeling that goes into those because it's my job to understand how things that obey the laws of physics behave. So those are stories. We are not saying this will happen. We are saying, if this happens, here is how the climate responds. So I think it's really important to be clear about the different types of models. Now, when we talk about tipping points, like you can't just like go into a climate model and say, put in tipping point, go. Climate models show you how the Earth system responds according to our best understanding of the laws of physics and chemistry. Now, those models get more and more sophisticated as they include more and more processes and operate on smaller and smaller scales, sort of better and better resolution. But the thing to understand about climate models is that you don't just say, put in the feedback. So you don't just say, put in the tipping points. Those things emerge as you let the laws of physics evolve everything forward. Now, the reason we don't understand where a tipping point might arise, for example, is because they arise from the interaction of a whole bunch of different things. And that is where the complexity in a climate model comes from, as opposed to the complexity in an integrated assessment or an economic model. The complexity in those models arise from the fact that people are hard. Does that make sense?
People are hard indeed, and physics is fascinating. Thank you so much, Kate. Okay, one of the things that really resonated with folks was the storytelling aspect. I think you so beautifully wove the storytelling thread throughout the whole talk. And so there are questions about someone who's a communicator looking to make the jump into climate change work. What are the needs there in that space to spur climate action? And this might be going more into the non-physics realm, but I think you have a really interesting vantage point into that space as well.
First of all, whoever asked that, I'm so glad that you are thinking of making this shift. We need you. Thank you so much. Welcome. There's kind of, I was going to say there's good news and bad news about climate communication. Actually, I think it's all good news. I think the good news is that we need you. The good news is that there are so many different stories to be told about the climate system. And having your perspective, having your ability to think through what are the interesting stories that can be told, I think is so useful and so valuable. I do think that there are some stories that get frequently told about climate change that suck, and I'm sick of them. For a really long time, there was only one story that got told, which was, all of these scientists say that it's happening, but this one guy says it isn't, and he's wearing a suit. So why don't you guys fight with each other? And that story is boring. It's not very representative. It's not very good. And I am really, really sick of it. But I understand where it comes from. I understand this need to have complexity and conflict in the stories that we tell about climate change. But I think that story has run its course. I don't want to tell that story anymore. I don't want to participate in that story. There's another story that I think gets told a lot, which is that climate change is inevitably going to be the worst it could possibly be, and that's punishment because people are inherently bad. And maybe, I don't know, I'm not a metaphysicist, I'm not a theologian, I'm not a philosopher, but I would like to try to not be inevitably bad. And I think there are a lot of people who would also like to try to not be irredeemable. So I think there's a lot of room for stories that incorporate solutions, not because we need to be Pollyanna-ish or we need to be hopeful, because I have a really complex relationship with hope, but I think the science supports the fact that we can bend the curve. We can create a better future. We can limit warming. And that story kind of sucks, saying like, oh, well, it's not going to be as bad as it was going to be, but we can make it slightly less bad. But you can also tell the story about all of the incredible co-benefits of climate solutions. You can tell the story about how amazing it is to be part of the community of people working on this. Because honestly, never before in human history has there been such an enormous movement of really awesome people all around the globe working toward the same goal. And I feel really, really privileged every day to like get to hang out with the people that I do. So I think there's room for stories there as well.
Oh, I love that, Kate. And I think it's really such a great invitation to everyone listening to think about what their story can be and what story they want to tell. And actually, that's another question that people are asking. Folks are wondering, what are kind of the top 3 things or the number 1 thing that you would ask folks on this webinar right now or watching it later to think about and to do? Like what's your ask of them?
Oh, that's such a good question. I should have prepared for that. I think, I like Drawdown is a great organization. We are one of many great organizations working on this challenge, but I do think Drawdown has an amazing communications team. It has an amazing labs team. It's got amazing people working here who are thinking through the questions that I have, that probably a lot of you have, which is, how do I actually make a difference? We all know, like, okay, there are things we can do. We can stop driving as much. We can use, better light bulbs, blah, blah. But Drawdown has really great materials for people who are kind of ready to take the next step. They have this series, Every Job is a Climate Job. So even if you are not working in climate tech, even if you are not a climate scientist, you can drive climate action at your work. And they have amazing guides for that. I would recommend just looking through the solutions library. You will probably see and maybe even fall in love with a solution that you didn't even know existed. So I think it's a combination of becoming better informed, but also realizing that you don't have to address climate change as an individual, because none of us are individuals. We're all plugged into wider networks, bigger communities, and that's our superpower.
Oh, thanks, Kate. Yeah, we are stronger together and better together. I love that. That's so lovely. Okay, I'm looking over here for a moment because there are, and I just want to let everybody know there are like 100 questions here. Thank you for being such a thoughtful audience. And I am awkwardly trying to read some of them. Huge gratitude to Todd in the background. So here's some science. Let's get back into science for the last few minutes, because there's lots of stuff that I think you with your physicist brain can really help us understand, Kate. Geoengineering is fraught with unintentional effects. And this viewer says it's a measure of our desperation that we're thinking of dumping huge amounts of chemicals into the ocean to fix it. Why is that? Why is that happening? What do you feel is going on in that geoengineering kind of Pollyanna view?
I mean, I think, I kind of want to defend some of the folks working on carbon dioxide removal here. I don't think they're all kind of, the brain from Pinky and the Brain. Am I dating myself with that response? Like, I don't think they're all, mad scientists bent on world domination. But, I think there are a lot of people who are justifiably very freaked out by where we are now. Because we have no geoengineering is not an option because we are geoengineering the climate right now. We have emitted 1.5 trillion tons of carbon dioxide in the atmosphere. That is having an effect. So right now, like the climate is changing. It is changing due to human activities. The National Academies, I think Elizabeth can post these in the chat, has some really great summary documents of where we are in terms of the research on carbon dioxide removal methods based on land, so direct air capture, reforestation, afforestation, enhanced rock weathering, but also some of these marine carbon dioxide removal methods. Most of my colleagues who are working in marine carbon dioxide removal say, we should assume that this is not going to work. We are trying to figure out how the ocean works. We are trying to figure out what to do about this, but we should assume that this is not going to take sufficient carbon dioxide out of the atmosphere. And we should never let this be used as an argument against cutting emissions as quickly as possible. Now, when it comes to dumping a bunch of stuff in the ocean is changing right now due to human activities. The ocean is becoming much more acidic, and that's because the ocean is taking up carbon dioxide. That's making it more acidic. There are some arguments that, okay, well, we can counteract that by dumping a bunch of antacid into the ocean. That will counteract ocean acidification. That will also force the ocean to take up more carbon dioxide. Understandably, the thought of doing something like that on a large scale freaks a lot of people out, including most of the people who work on it. But you're right that this is kind of a Hail Mary act of desperation because of the geoengineering that we have done so far. The carbon dioxide, the methane, the nitrous oxide in the atmosphere, and the resulting acidification of the oceans. So that was a very long-winded way to say it's very complicated. There's no easy answers here, but I hope I touched on some of the important points there.
Oh, thanks so much, Kate. We've got another layer to you here that folks might not necessarily know about, which is your connection with the US federal government. And so there are some questions from folks about, are political leaders aware of the science? It seems that everyone from all political sides, could work on cutting emissions if they were aware of the science. Tell us about what levers you're pulling in the political realm in the US.
So I'm the chapter lead for climate trends on the forthcoming National Climate Assessment, which will probably get released this fall, October or early November at the very latest. And that has been a really lovely experience working with some of the smartest climate scientists in America to try to put together a report really laying out what's happening and more importantly, what we can do about it, because we don't want this to be yet another report where the scientists say it's really bad, and then there's like 2 days of news coverage saying it's really bad, and then nothing happens. We want to really tie this to there is action that we can take. Here are the things that we can do. So that's something that we've been trying really hard to do. I actually, Elizabeth, kind of disagree with the suggestion that, oh, if only folks knew the science, they would act upon it. I'm not sure that's the case. And that kind of goes back to the first question about how do we communicate about this? Because people, and I really include me in this statement, people don't react to science nearly as strongly as they react to stories, as they react to narratives. And right now, I don't think the debate is about, is it happening or not? Is it real or not? At least not at high enough levels in the government. Everybody knows it's happening. It's just a question of whether they can see themselves and see their communities in a solutions-oriented future or not. And I think that is really the important thing, because we can get out, we can explain science over and over and over. And the thing that's really, really going to move the needle is narratives.
Thank you so much, Kate. With that, I'm actually going to bring Todd, our Director of Marketing and and Communications, on to talk a little bit more about that. Todd, welcome.
Hi there. I just want to pop in from behind the scenes really quick to say thank you again for the amazing questions. We're capturing all the questions behind the scenes, and we're going to ask Kate if she would generously offer a little bit more of her time in the follow-up email that we send out early next week with a recording of this presentation to answer some of those questions that we're seeing pop up in the Q&A. So just want to let you all know that we're capturing those questions. We hear you, and we don't have a lot of time today. So back to you, Elizabeth.
No, thank you so much, Todd. And thanks, everybody. As we wrap up, a couple things. We will send an edited recording of and when I say edited, just cutting me out at the beginning. No, folks don't need to see that. Just like, let's start with Kate. We'll send that out to everybody who is registered. So if you're here, you were registered, you're going to get that. And please feel free to share that widely. We also will post it on our YouTube channel. That's where, if you're interested, you can go back and look at previous Ignite talks also. We will have a talk in September. Stay tuned for that. If you clicked that you wanted to be part of our newsletter, you will get information about that. If you didn't click that you want to be part of our newsletter, please sign up. I just posted the link in the chat. We will also make sure that all of the links that we shared, including the Bloomberg one, which I apologize, folks, that one is behind a paywall, but it has incredible data that Kate personally contributed to. We'll make sure that all of those links, as well as answers to many of the questions, to some of the questions that folks asked, are in the follow-up email. With that, Kate, do you have any last words you want to share with the folks we had? We had over 500 people today. It was such a pleasure to have people from all over the world learning from you.
I just want to say thank you so much. I know your time is valuable and we're all really sick of Zoom. So thank you very much for taking the time. I really, really do appreciate it.
Okay, everyone, let's give Kate another virtual round of applause. So much gratitude. We are so grateful for you, Kate. Thank you for stepping in and helping us write the next chapter of life on Earth. Thanks all. Really appreciate you. Take care and be well.